Your speaker is not, now that's not good at all. It keeps doing that. Good. I don't know what to do. Check my speaker. I don't know what to do. Check my speaker. Oh, gee.
Input level, volume, test speaker.
Maybe it'll be okay. They heard me last time, okay?
Yeah, they did.
My meeting. Join audio, share screen, invite others. I don't know what to do. It says recording.
Yeah.
Testing 1, 2, 3. Is anybody? Hey, that's good. Whatever you did, that's good. Is anybody out there? Earth calling Thermo students. Earth calling Thermo students. Come in, Thermo students. Nobody's reporting in. We need students. Where are you? Hey, Kristen, yay! It says click to share screen. I don't know if I want to click to share screen.
Hey, do you click the share screen button? Okay. Oh, and then I'll pin his video, right? Well, that one doesn't have a.
I think
that was for.
I think that's pretty good, just like that.
Oh, unpinned video. No, I guess he's pinned.
I guess we're okay. Yep. Kristen, how are you?
Love you. She can't talk back to you. Her mic's muted.
Yeah, her mic's muted. Well, I wonder if I'm supposed to unmute or something here. Manage participants, it says. Oh, we only have Kristen so far.
Yep, just me.
Just you. You're the faithful one.
Yep.
Well, good for you. Man, I am so sleepy. I could take a nap right now. Would that be all right?
I mean, that's what I would like to do right now. I am so tired. I don't even know why. Like, I am just like, ugh. And I've got to work tonight still.
Oh, no. What kind of work do you do?
I'm a prayer minister.
Well, bless you. Yeah, that's good.
Yeah, I've got to work. But yeah, I'm thinking after this class, I'm gonna take I don't work till 4:30.
Yeah.
So I mean, like if you want to cut it a little short or something, I won't be mad at you, and then I can take a nap.
That sounds good. Hey, we've got Levi here too. Good going, Levi.
Hi, Mr. Griffin.
Yeah, good to hear from you. And there's another important person right there. Rebecca Griffin, yeah. That's my daughter, Guru. And Jackson Wilson, yay. Well, we're early, though. We're 5 minutes early. And there's Jackson. I think we're doing okay. We're going to talk about cycles today. That's the big topic. Yeah, a little bit of review. There's basically 3 kinds of cycles. And we're going to be moving into the Rankine cycle muy pronto. What's today? Tuesday, Thursday, we'll be doing the Rankine cycle for sure. Hello, Rebecca Griffin. Can I click on you? What happens if I click on you? Nothing?
Thanks for holding. How can I help you?
Hey, I was just checking out your video.
Oh, good for you.
It looks good.
But there's no, I can't get a picture of you on here.
Let me see.
Well, he's just going to come up to the
Here-
parking lot and let us know he's here, and the pharmacy will run them out to him.
There
But
she
just a heads
is.
up, you might want to let the pharmacy know that he's coming and give them permission to give him the pills. Now,
There-
they don't open back again until
There's my daughter, guys. There's my beautiful daughter. Fellas, too bad. She's already married. It's too late. But there she is. But there's no video, Rebecca. What happened to the video? I mean, the audio.
I just muted
understand.
myself.
Oh, okay. Well, maybe I should get my whiteboard back on here. I think I'll be okay. Yeah, there I am. Hey, it's almost time for class. I guess I could launch into a fascinating talk about cycles. And there's Brandon. Yay, Brandon. Brandon's with us. Okay, well, let's review the three kinds of cycles, shall we? There's three basic types. There's three types of cycles. Hey, that would be a good final exam question. Well, what are the three types of cycles? Yeah. Well, there's power cycle.
Heat cycle, refrigeration cycle.
Yeah, there you go. Refrigeration cycle.
Sorry, my computer's about to go down, so I'm trying to plug it all in.
Hey, there's I thought that was Dawn for a second.
Yes, sir.
Yeah, good. Well, plug in your power cord and charge it up. And then
Sorry, I didn't mean to interrupt.
You're fine. There's a heat pump. There's the heat pump. There's the three kinds of cycles. And let's just do one here and see if you guys remember how to do this. I'm going to draw the schematic for a power cycle. The topic right now is cycles. And I'm going to draw a power cycle now. And the way I like to draw them, I kind of have a feeling I'm going to sneeze. So watch out. It could happen at any time. Oh, gee, there's somebody on my phone. Just hang on. See what they want. I just turned them off. I don't know who it was. Probably somebody that wants money. Okay. This is how I want you to draw your cycles. Here's your low temperature. Here's your high temperature. This is going to be your power. Well, boy, they don't give up easy, do they? Yes, hello. Yes. Oh, I'm fine. I'm right in the middle of a distance learning lecture. Can I talk to you later sometime? Oh, okay. I thought I sent them to you. That's where I sent it. I'll try. I'll try again. Thank you. Okay. All right. Now, where were we? Always somebody wanting me for something. Okay. There's the low temperature heat transfer rate. And there's the high temperature heat transfer rate. And that's the power. And I'm going to give you the numbers here. 800 BTUs per minute. And I'm going to ask you guys to do something with these to see if you remember what to do. That's 600 BTUs per minute. And so this would have to be 200 BTUs per minute because you've got 800 coming in and 800 going out. Can you see that? So it kind of makes sense. Okay, now this temperature here is 300 Fahrenheit, which is 760 Rankine roughly. And this one is, I feel that sneeze coming on. 60 Fahrenheit, which is 520 Rankine. Now, what I want you guys to do, I'll be quiet for a couple of minutes and let you work on this. I want you to find the actual efficiency of this power cycle. This is a power cycle. See, we're going to be studying the Rankine cycle, the diesel cycle, and some others power. We're going to be studying power cycles. And this is the symbol, this is a Greek letter eta for the reversible. If this thing ran reversibly, I want you to find the efficiency if it ran reversibly for the reversible cycle, and then the actual efficiency. And I will hereby shut up for 2 minutes. And I want you to find those on your mark. And get set, go. If you just tuned in, I'm having my students find the efficiency of this power cycle. Let me see who's just tuned in here. Well, we got Daniel. Hello, Daniel is with us. Abdullah and Don. Good deal. We got a good crowd here. And there's Coy and Kristen, Levi, Mark, Tyler. Good. We got a good group here. And we're trying to find the efficiency, actual and reversible, of that power cycle. You should be done if you have the equations handy. Well, that's probably enough time. Now on the actual, it's just the power divided by the input heat transfer. Well, these are rates. It would be a 200 over 800. I can do that in my head. That's 25%, isn't it? 0.25, did I do that right? 2/8, yeah. It's 0.25. But now the reversible See, you could write this as the QH dot minus the Q. This is how I remember it, over the QH dot. See, that's 800 minus 600 is 200. Divided by 800 gives you 0.25. You could write it like that. Now, the equation here for the reversible efficiency, it sort of mimics this, only these have to be Kelvin. They have to be Kelvin. So if you do the Kelvin, what's 760 minus 520? That's 40. No, that's not right. Is it 140? Yeah, I think it's 100 and. Oh gosh, my brain is jello. I think it's 140. No, it's 240. It's 240. This numerator is 240, and the denominator is 760. And now we're going to get the efficiency if the thing ran without any irreversibilities. It would be we would get 0.3158 31%. If this thing ran perfect, you'd get 31% efficiency, but you don't. A real engine will never give you the maximum. That would be the maximum possible. Now, the way it works, guys, this is always less than that. Does that make sense? The actual, it's going to be less than the maximum. Now, well, as long as we got these numbers up here, let's look at Clausius's inequality for just a minute. If you remember, Clausius said in a cycle, he said, this here is less than or equal to 0. That's known as the Clausius inequality. Now you could put a dot over here if you wanted to. And we're just going to go ahead and see if his inequality works. Okay, now what is, if you go all the way around the cycle, it looks to me like you got 800 BTUs per minute at 760 Rankine. We probably should put in our units. We're plugging in the Clausius inequality. Now that's positive because it's coming in. It's coming in. So you got your refrigerant here. Well, no, this is not a refrigerant. A power cycle, it'd probably be, well, it could be lots of things. It could be steam, for instance. But now see, this is going out. So that's going to be a minus 600 over 520. Now we're going to see what that is equal to. And I have a hunch it's going to be less than 0. See, Clausius did this for hundreds of steam engines, and his inequality always worked. I'm going to try it. 800 divided by 760 minus 600 divided by 520. Boy, Jove, I got a negative 0.101 something. Hey, it came out negative, just like Clausius said. Here, let me write his name there. Clausius. He examined, I don't know, at least dozens of steam engines, and that seemed to work for him. Okay, well, let's do another one. If you're happy with that. Any questions so far on that heat engine? Well, nobody said anything. Let's do a refrigeration cycle now. Now that was a power cycle, and we're studying cycles today. And now we're going to do a refrigeration cycle. Be sure to ask me if a question if you don't want this erased, because we're just going to keep moving along here. Okay, I'm going to do the same thing now. I'm going to write refrigeration cycle. This is going to be a refrigeration cycle. And when you do that, you draw counterclockwise. You'll discover this. See, we're going to study this in a little more detail. We're going to do some actual refrigeration, well, at least one refrigeration cycle here after a while. If you do this on a PV diagram, you'll see that it goes counterclockwise. Refrigeration cycles do that. Everything's kind of backwards. The heat transfers are going the opposite way in a refrigeration cycle. We've had this before, but I got this theory that sometimes students need to be reinforced by repetition to where they'll get this. Now, the power has to go in this time. See, this is going to be the power. This is your heat transfer rate in. Heat transfer rate out. Now, let me give you some numbers, and I'm going to let you guys figure something here in a little bit. This is 25 Celsius. And this is minus 10 degrees Celsius. This here's 150 watts. And this is 200 watts. Don't get that W there that's watts mixed up with this W dot. That stands for power. Those are so different. Do not get confused. Now, I want you to think about this. If you got 150 going in and a W dot going in and it makes 200, hey, bye-bye for now. What is this going to have to be? I want you to think and think and think.
50.
Yay, we got 50. Good going. Because see, 50 watts plus the 150 watts going in can give you 200 watts going out. Yeah, that makes sense. Here's what I want you guys to do. We got a little room over here. They don't call this efficiency. They call it beta. There's an actual beta and there's a reversible beta. This here is a...
Be 3, wouldn't it?
I'm sorry?
I was just saying, I think it would be 3.
Gee, you're fast. I hadn't got there yet.
Sorry, sir. Sorry.
No, that's fine. It might
Jumping
be.
the gun.
Here, let me do it. I'm going to do it now. And by Jove, it is 3. But you haven't done this one yet, have you?
No, sir.
Go ahead and do it. I'll wait. Man, I'm so sleepy. Any of you sleepy?
Yes, sir. I was up till 7 this morning, and then I slept from 7 to 10.
Well, right now, for anybody that just tuned in, we're finding, I call it the beta, but what it really is the coefficient of performance if this refrigerator ran perfectly. That's what we're trying to find right now. Now try to remember, guys and gals, you got to use Kelvin. You can't use Celsius. There's Abdullah. You have to use Kelvin or it won't work.
I ended up with a tad over 8.5.
How much?
8.518 or 519.
You might be right. That's not what I got. Let's do it together here. That's not what I got. Now, see what this is.
Oh, I did it wrong.
Well, we'll do it again. I might be right. See what this is QL dot divided by QH dot minus QL dot.
I accidentally did the high temperature. I got 7.52 this time.
That's well, I got 7.5. I wonder how come you got a 2. Maybe I rounded off. I bet you're right.
Were you using, did you, for Kelvin, did you do 263 and 298?
Oh yeah, I think I was just a little bit sloppy. I tell you what I did. I did 263 and then I did 35. The 263 you get by taking
That makes sense.
right over there. You take 25. It's really 273.15, but I just lopped that off and I got 298. I think. Yeah, I got 298 for the 25. And so now I forgot what I was doing. But the low temperature is it's not exactly 263, is it? It's 263.15 to be nitpicky about it, huh? And I was just a little bit sloppy. Here's what you get. 263.15 divided by 35. I'm getting 7.5, rounded off to 2. If you just have 263 divided by 35, you get 7.51. Let's don't fight over it. It's just a matter of being nitpicky about that 0.15 business there. But there's your, they call it the COP, coefficient of performance for the refrigeration cycle. Notice it's much bigger than the actual. See, this is the maximum. You get your maximum coefficient of performance with no irreversibilities, and the actual will always be smaller than the maximum. 3 is smaller than 7, so we're in great shape. Now let's examine this with Clausius's inequality. Let's do that. Okay, I need a little room to do that. Where's some room? How about right here? This will work. We figured this out here. It's 7.52, something like that. We got a little room here. Now remember, Clausius inequality says if you go around a cycle, you go around a cycle, this is less than or equal to 0. Of course, it'll be less than or equal to 0 if you put a dot over it too. In our case, we have a rate. See, without the rate, it's not a rate, it's just a heat transfer. But if you put a dot over it, it's a heat transfer rate. And let's try it. Now, we got going in is positive. Heat transfer going in is positive. So we have a 150 watts divided by, now you can't use Celsius, you have to use Kelvin. being lazy, I think I'll just go 263 Kelvin. That's positive because it's going in. Hey, but now see, this is going out, so that's minus 200 watts divided by, that was the 298 I think we had a while ago. 298 Kelvin. Now let's see what that is. Okay, I'm going to do that. Here goes. We're doing Clausius's inequality. 150, 263 minus 200, 298. Boy, Jove. Of course, it has units of watts per Kelvin. But do you notice it's negative? It's negative because it's got irreversibilities. Clausius equality always works. It's the basis for the second law. Clausius inequality is an empirical equation. Let me write that for you. Is there any question on that? I'm going to erase it. Is there any comment or question?
No, sir.
Okay, well, I guess you're happy. Came out negative, that's good. Now see, if it had come out equal to 0, then we would have had a reversible cycle. It would have given us the maximum possible cooling of our hot dogs and our milk and our frozen pizza. Now, what was I going to do? I forgot. Let's see. Anybody know what I was going to do?
You were telling us about how it's the basis for the second law.
Yes, that's what I'm going to do. I'm going to talk about the second law now. I'd like you to understand the second law and where did it come from. And this is explained in your book, but I know of students that read this wonder, well, what are they doing that for? It's on page 191, and it's based on the Clausius inequality that we know and love. And I've given you little sermonettes about it before. See, when it's equal to 0, whenever you have a quantity that you go all the way around a cycle and you come back to where you started and it doesn't change it any, you got yourself a property. See, pressure is a property, specific volumes of property, temperature is a property, little u, little h, those are all properties. And if you go around a cycle and look at the change in pressure through each process, add them all up, plus and minus, you'll get 0 for the cycle. See, if you take and do all the changes in pressure, just pressure, there you go, you'll get 0. And if you do all the changes in specific volume in a cycle, you get 0 because they are properties. They depend on their state and not the path. But see, there are things that depend upon the path, like, for instance, work. The amount of work you do depends upon the path. See, you can go from state 1 to state 2 on a PV diagram. Different ways. You can go like that, or you can go like that. Did you know that the work is different It depends on the path, doesn't it? Can you see that? Because the work is the area under the graph, and the area under this process here is smaller than the area under that process there. See, work is not a property. Temperature is. If you go from 1 to 2, the change in temperature doesn't matter. It doesn't matter whether you go meow or you go meow. The change in temperature is the same for any process between 1 and 2. Think you understand that? Now here we have something that's kind of weird. You've got something that's not a property. Heat transfer is not a property any more than work is. If you take and add up all the changes in the heat transfers in a cycle, it's different. It's not zero for one thing, and it's different depending on which path you take. But here's something really weird. You've got something that's not a property divided by something that is a property, but if you have a reversible cycle, it's equal to 0. That means this thing is a property, and they decided to give it a name. They called it entropy. They call it entropy. They gave it a symbol, and they said that entropy, the change in entropy is equal to this, but now the catch is it's got to be a reversible process. Now, if it's not a reversible process, then this is going to be less than or equal to 0. See, it's equal to 0 if it's a reversible process, but if it's an irreversible process, it'll be less than 0. Well, I've told you all this before. I don't know if it's sunk in, but we're gonna take a cycle now. We're talking about cycles today, and we're gonna do some more here, and we'll start on our Rankine cycle here later. But if you take a PV diagram, and this is on page, I think it's on page 191. Yeah, you could read about it. And we're going to take a state 1 and, I don't know, state 2. Here we go. There's state 2. And we're going to go from state 1 to state 2 along path A. There we go. Put a little arrowhead on there. And it's going to be a reversible process, solid line. And then we're going to come back like that. This is going to be process B, another reversible process. And we're going to add them up. Here we go. If they're both reversible, and we're going to add these up, and we're going to use Clausius's idea here. And if you go for the whole cycle, what you'll have is 2 processes. You'll have this one here for process A, and then you'll have this one here for process B. And if they're both reversible, which they are, then that will equal 0. So far, so good. And we're gonna label this going from 1 to 2, and we're gonna label this going from 2 to 1. Here, let me make that a little nicer. Yeah, this will be going back from 2 to 1. See, we're gonna go from 1 to 2 on process A, and we're gonna go from 2 to 1. We're gonna go back. You've got yourself a cycle. They're both reversible. Clausius says it's 0. And now we're going to introduce an irreversible process. we're going to go from 1 to 2 differently now. Irreversible processes are dashed lines. That's an irreversible process. There's an old joke here. It's time for an old joke. See if you can figure out what this is. See if you guys can figure this out. Okay, the floor is open. This is a joke now. It's got nothing to do with Clausius. What is that? Nobody knows. Okay, what that is it's a column of ants entering a whiskey puddle. That's pretty good, isn't it? It's a column of ants entering a whiskey puddle. All right, well, enough of that. We don't have time for jokes. What this is we're going to call it process C, and it's irreversible process. How do you spell reverse? IBLE, you suppose? I think that's right. Okay, and now what I'm going to do is I'm going to write the cycle here using Clausius's idea. And what that's going to be is we're going to go from 1 to 2 on process C. This is all on page 191. You could read it if you wanted. And then we're going to go back. We're going to make a complete cycle. We're going to go back from 2 to 1 on process B. But see, process C has some irreversibilities. So on this cycle, you don't get 0. It's less than 0. That's what Clausius says. He says that for a cycle, this thing here will be less than 0 if there's any irreversibilities in the cycle. Now we're almost done, and we're going to have our second law, and it'll be worth spending this 10 minutes on this to understand the second law and where it came from. It came from Clausius's inequality is where it came from. Now watch this. We're going to do some algebra now. We're going to take this stuff here, and we're going to subtract it from this stuff here. Okay, well, when you subtract this from this, what you get is this here. I'm probably putting some people to sleep. I wouldn't doubt it. And see, when you subtract it here, what you get is this here. Now, when you take this and you subtract that, you get nothing because they're identical, aren't they? They're the same. They go bye-bye. But now watch this. This is clever. When you take 0 and you subtract something that's less than 0, well, that
Get a positive number.
this is a little confusing. There's a less than sign here, and when you take this and you subtract with a less than sign, you get a greater than. The only thing is, it'll be greater than 0. It won't be less than 0. I wonder if I could explain that. Kind of hard for me to explain.
Just double negative.
Yeah, it's kind of a double negative. I don't know if you've ever dealt with inequalities much, but when you subtract this from that, because that's an inequality, it switches when you subtract, and it's a greater than. And so here we can write this like this now. This will be greater than this. Now this we've defined earlier when we had a reversible process. That's precisely equal to S2 minus S1, or you could just say delta S. And we're almost there, guys. The second law for control masses. I wonder if there's room. Yeah, there's a little room here. We can write this as delta S. Instead of a greater than sign, we're going to make an equal sign. And we're going to go here and add a positive term. And we're going to give that a name. We're going to call it generated entropy. We have just shown you where the second law of thermodynamics comes from. Now, this is for control masses. For control volumes, you have a couple of other terms. You have mass coming in and mass going out, so you have a couple other terms. See, mass has entropy, just like it has other properties. Mass has temperature. Yeah, you take a rock, it's got a temperature. Well, guess what? That rock has entropy too, because entropy is a property, just like specific volume. Take a rock, it's got specific volume. It's a property. It's got temperature. And what else does it have? Well, lots of properties. We have just shown you where the second law of thermodynamics came from. And this is always going to be positive because this here is going to be bigger than zero. So when you do this, this will be bigger than that. If you want to make it equal, you got to add a positive term. Do you remember me telling you? Let me make a little room here.
Were you saying that the S generated is always positive, sir?
Yeah, that's exactly what I'm saying. Here are the three possibilities. This is S generated, or you could have little s generated, doesn't matter. All that means is the entropy per mass. If it's equal to zero, you have a reversible process. If the specific, what's the name of that? The specific generated entropy is bigger than zero, you have an actual process. It's irreversible. Like most actual processes, if not all, are irreversible to some degree. You can approach reversibility, but the example I did with you guys, do you remember when we had our perfume that I cut loose in your classroom there, the blooming, oh, what was the name of that perfume that I had?
Something jasmine. I think.
Yeah, night blooming jasmine. Yeah, I poured it out on the table there, and it's an irreversible process. That perfume does not go back in that bottle. You're not going to get it back in that bottle either. It's an irreversible process. So you're going to have a generated specific entropy bigger than zero. Now, if this happens, if you got a generated specific entropy that's less than zero, then you have an impossible process. It can't happen. It's an impossible process. Never been done in the laboratory. Now, if you're able to do one of these in your garage over the weekend, you give me a call on Monday because I want to know about it. Mr. Griffin discovers a generated specific entropy less than zero. I don't think you're going to find it.
Nobel Prize 2020.
Yeah, that's right. It's Nobel Prize time. Exactly. Okay, well, we had a little review there, and it's time to talk about the Rankine cycle, I think. Now let me dig around here and talk to you about the Rankine cycle. Is there any other wonderful or not so wonderful comments of any kind, questions? I'm listening from anybody. Well, nobody said anything. We're going to talk about the Rankine cycle now. All right. We talked about the second law. We talked about the three types of cycles and Clausius's inequality. And now the big topic now is the Rankine cycle. Now I'm sitting here in this room and there's lights on, and you can see this board because the lights are on in this room. And guess what? The lights in this room come from a power plant. Well, there's several. There's one out by Coweta. There's a grid. I think the Keystone Dam produces electricity too, but that's different. That's what they call hydro something power. The one out by Catoosa, they're burning coal. And guess what? They're doing it in a Rankine cycle. The Rankine cycle is the cycle that powers our electricity in this country. You like electricity, you like to turn on the lights. Well, it comes from a Rankine cycle. Now, what is the Rankine cycle? Well, it has two isotherms and two adiabats, I believe, but I don't want to lie to you. Let me look this up. It's got two adiabats and two isotherms. Let me dig around in the book here. Hang on, I'm going to find it here. Now, this is in chapter 9. We omit chapter 8. We don't do chapter 8. So let me write that down. We omit chapter 8. Now, over at TU, they include chapter 8 in their thermo class, but OSU does not. And basically, chapter 8, what it is it's kind of a shortcut. They take the first and second laws and they blend them together and they come up with an equation that's kind of a shortcut. But you can do anything with the first and second laws without using chapter 8. And so we follow OSU. We do what OSU wants. So we don't do chapter 8. Okay, now the Rankine cycle, it's on page, well, it looks like 258. And it's got 4 processes. Two of them are adiabats. And 2 of them are isotherms. That's not how they expressed it. They called it constant pressure, and so I'm wrong. Let me get this right. I'm just not thinking very good today. It's 2 adiabats and 2 isobars. I was wrong. Now, I was partially right in that part of those isobars inside your vapor dome are also isotherms. So there is some isothermal process going on, but let me draw you a picture of one. Now we're going to do a pretty simple one, I think. There's several different models here. Let's see if I can find the one I like. This one's pretty good. This one's on page 265. And it's going to look like this. Only they do a TS diagram. So let's do what they do. We're gonna have a TS diagram. And we're going to have an ISO. I don't like 265. Just a minute. Let me find one that I like better. The one on 258 is more to my liking. And it kind of goes like this. You've got a isentrope. Well, it's an adiabat, but it's a reversible adiabat. We're going to have a reversible, we're going to have all of our processes be reversible. Makes it easy to calculate. We have a reversible adiabat. And they decided to number it over this way. Here, now here's your condenser. And that's an isobar, see it? They call that the condenser. That is the condenser. And they decided to label this 1. And here's your pump. Now the pump is also a reversible adiabat. The other name for a reversible adiabat is an isentrope. I think I told you about those. That's when delta S is equal to 0. So this will go straight up to state 2. And then you have a another isobar. Now that's the pump. And here's the isobar. And they kind of go like this. And in here is that, why am I so wiggly? Why can't I draw a straight line? There we go. There's your state 3. And see in here, this is an isobar. No, that's not state 3. State 3 is up here. There's state 3. This is an isobar. All the way from 2 to 3 is an isobar. It's the boiler. Did you know that boiling is isobaric? Get yourself a pan of water, put it on your stove, turn the heat on, and it'll boil after a while. Guess what the pressure is? Well, it's atmospheric pressure, right? And the pressure will stay the same while you boil that water. It's an isobaric, boiling is isobaric. So you got your pump, you got your boiler. Now here's where you got the turbine. And it's the turbine that gives you what you want with the Rankine cycle. It's going to give you the power. See, a turbine spins those turbine blades, which turns the electrical generator, which gives you the electricity, and they send that out on these transmission wires across the country to our houses. The turbine and the pump are isentropes. They are isentropes. The condenser and the boiler are isobars. So the Rankine cycle has 2 adiabats and 2 isobars, and all of them for the ideal Rankine cycle, which is what we're studying, we're studying the ideal Rankine cycle. All of them are reversible. Okay, great. Now you know what a Rankine cycle is. Now they have lots of improvements to the Rankine cycle, and they can make it more complicated in an effort to give you more electrical energy per ton of coal that they're burning. If you want to see how complicated it can get, look on page 271. They have two different turbines on page 271. And they have some other little features here to give, they're trying to get just a little bit more power per ton of coal that they burn. See, they burn a lot of coal. I don't know if you've ever been on your way to school and ding, 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 here comes the train, and you have to stop. You're already late for your class, and this train comes along, and it's got coal cars, 110 of them. Swish, 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 swish. You count them. There's 110 that go by. Finally, the thing goes back up, ding, 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 and you can go and be about 15 minutes late to your class. Can anyone relate to that?
Had it happen once or twice.
It's happened to me. Well, can you imagine trying to pay for the coal in just one of those cars? There's 110 of them. I mean, if you could get a more efficient power cycle. Remember, we talked a little while ago about the efficiency of a power cycle, and remember what it was? It was the output W dot over the input QH dot. The output power is what you're after with a power cycle, and the input heat transfer rate, you got to pay money for that. That coal costs money. They dig that coal in Colorado. Now, we have lots of coal here in Oklahoma, but it's got sulfur in it, and it causes pollution. It gives you things like sulfur dioxide. It smells like rotten eggs. Down by Dewar in central Oklahoma, they have coal mining, but it's just got too much sulfur in it. So we buy our coal from Colorado. It's high-grade coal. There's not much sulfur in it, burns clean, but it costs you money. Can you imagine if you could make a Rankine cycle that was 1% more efficient? That's one of those cars full of coal. So that's the name of the game, trying to get more energy for your buck. Okay, so now we're going to start us on a Rankine cycle problem. And let me see which one it is here. It's going to be problem number. Totally organized as always here. This is going to be problem number, well, it'll be in chapter 9, because that's what we're studying. It's 913. We're going to start on problem 913. I just need some room to work here. Let me get rid of all this and let me put 913 up here and see what we can do. Okay, let me find it now. 913. All right, it says here, steam power plant produces 10 megawatts of net work. Well, we probably should write some of this stuff down. The network is 10 megawatts. Okay. Steam flows at 5 megapascals, 500 Celsius to the turbine. You know what? Right here, that's state 3, isn't it? In other words, the temperature at state 3 is going to be 500 Celsius. And the pressure at state 3 is 5 megapascals. I'm writing down the stuff they're giving us in the problem. We are looking at problem 913. The condenser operates at 50 degrees Celsius. Well, see, this is state 4 here. In state 4 and state 1, the condenser goes from 4 to 1. So the pressure at 4 and the pressure at 1 are the same. And they are, no. It's the temperature. The temperature at 4 and the temperature at 1 are 50 degrees Celsius. They want to know the mass flow rate. They want us to find m dot. That's what they want. Well, we're going to make us a little table here and get started on it. Hey, I figured out how to grade your papers, or almost have it figured out. I'm not quite there yet to assign you stuff that I'm going to grade, but I will be probably this weekend. I'll be starting to assign you guys problems that I'm going to give you some grades for. I want to put this where I can see it over here, out of my way here. Oops. Do a little fudging there. There, I can see all that better over there. I just need some room to work here. We'll get a few of these. And what we're going to do is, we've done this before with the Carnot cycle. We're going to have our processes here. Uh-oh, I'm kind of running into my T's here. I wonder if I'm going to have enough room here. I think so. Remember doing this for the Carnot cycle. Okay. Well, we know that T3 is 500 Celsius. So that goes right here. And P3 is 5 megapascals. I'm going to put it in kilopascals. That's okay. We'll leave these in Celsius. That's fine. Now, what did they say this was here, this temperature at 4 and 1? I forgot. Did they say it was 50?
50 degrees Celsius.
How much?
50 degrees Celsius.
50. Good going. At state 4, we have 50 degrees Celsius. And at state 1, we have 50 degrees Celsius. Now, 2 of these processes are adiabats. From 1 to 2, that's a 0 because 1 to 2 is, well, it's an isentrope, but it's also an adiabat. It's a reversible adiabat. That's 0. And from 3 to 4 is an adiabat. It's the turbine. See, this is the turbine. Yeah, we could write that stuff down over here. 3 to 4 is the turbine. 1 to 2 is the pump. I haven't talked about pumps in this class. We need to talk about pumps. 2 to 3 is a boiler. I don't know if we've worked very much with boilers. And 4 to 1 is a condenser. Okay, now let's see. Did I do P3? Yeah, I think I did. T3, where's T3? Yeah, I did that. This work. 10 megawatts. See, that's the network though. That would be down here when you add up all the work per masses. Well, now wait a minute. That's not little w. I can tell by the units. That's big W dot, isn't it? See, this is a little w. But that's big W dot. I tell you what big W dot is. It's equal to m dot times little w. So this column here is work per mass, but they gave us the power. They want us to solve for this. We can do it. I'm not sure I want to do it all right now, but we could fill in some of them. Let's do some of them. Here's some anchor points on the Rankine cycle. You can count on that right there. See that state 1? That is called saturated liquid. State 1 is saturated liquid. So now let's dig into our textbook. Look up water and find the pressure at 50 degrees Celsius. Start digging. Okay, I think I've got it. At 50 degrees Celsius, it's really low. It's a low pressure of, I'm getting 12.350 kilopascals. Can you find that?
Yes, sir.
Yay, good going. Hey, we can get the specific volume there too. At saturated liquid, it's 0.001. dig around in your water table there and see if you can find that. And now we can get, these are all, guys, these are all initial values of your processes. Going from 1 to 2, that's P1, that's V1, that's T1. These are the initial values. And the specific enthalpy is at 50 degrees Celsius. It is 209.31. 209.31. Now what that is kilojoules per kilogram. And the specific entropy is 0.7037. It's really pretty easy. You just look this stuff up in the tables. It's kilojoules per kilogram Kelvin. And there is no heat transfer. We'll get the work here eventually. That's at state 1. Now, what do we know at state 2? Well, let's see. If 2 and 3 are isobaric, going from 2 to 3 is an isobar. Didn't we decide that? It's the boiler. Boiling is isobaric. Remember, you're in your kitchen, you're boiling water. The pressure just doesn't change while you boil that water. It's atmospheric pressure. Now, this isn't atmospheric pressure. This pressure is 5 megapascals. Holy cow, that's a lot more than atmospheric pressure. See, atmospheric pressure is 100 kilopascals. This is 5,000 kilopascals. What is that, 50 times? 50 times atmospheric. But we know what the pressure is at state 2. It's the same as at state 3. So we've got our pressure at state 2 and our pressure at state 3. What about the pressure at state 1? I know what it is. Look here. This is, I know this is a TS diagram. But inside the TS diagram, it's also isobaric, isn't it? And so the pressure at 4 is the same as the pressure at 1. Okay. Hey, I got an idea. Look here. We got P and we got T. PV equals RT. If you got P and you got V and you got T, couldn't we find V? What do you think?
Sure.
Somebody needs to say no. You can't. You can't go PV equals RT and get this V here. Why not?
Well, it's probably not behaving like an ideal gas.
Exactly. Exactly. It's not. In fact, it's state 2. What is it?
Saturated liquid. Or
It's a
condensed liquid.
It's a compressed liquid, isn't it? See, state 2 is a compressed liquid. And you can't use the ideal gas law. Well, I was using it at state 3 there. But just stay away from the ideal gas law entirely. You certainly couldn't use it at state 2 because that's a compressed liquid. So what do you do at state 2? Well, you could go to the compressed liquid table. Let's go to the compressed liquid table. Do they have one? Let's shop around. Yeah, they have one. Do they have a 5,000? By Jove, they do. But we need something else to look up. What other thing do we know at state 2? Don't we know something at something else at state 2 besides the pressure? We could look up some stuff at state 2 if we just had something else. What is this process going from 1 to 2? What is that process?
Thinking. Second.
It's a what? The process.
You said it's adiabatic.
Yeah, it's
And if
adiabatic.
and since this is ideal, or the one that we're doing is ideal, it makes it isentropic.
Exactly, it's isentropic. Well, what's isentropic?
It means that the change in entropy is equal to 0. So the
That's
entropy is
it.
going to be the
Okay,
same.
here's the secret, guys. This is going to be 7037. It's state 2. So we're going to go to our compressed liquid table, and we're going to look up 0.7037. Uh-oh, it's not in there. You're going to have to interpolate. But you can do it. Can you see that you could interpolate? I'll tell you
Yes,
what the numbers are. They have a 0.5708. No, 5705. And they have a 0.8284. And what we want is 0.7037. But we could interpolate. Yeah, we sure could. Somewhere around 60% of the way. And they have all the other properties there at 5,000 kilopascals. Are you guys on my page here? It says compressed liquid water at 5,000 kilopascals.
Yes, sir.
Excellent. Well, see, you can get the little v and the t and the little h. All you got to do is interpolate. You can see it coming, can't you?
Yes, sir.
Yay. Good going. Well, I'm not going to do it. I'm going to let you do it. But I think I've shown you how to get this one here. Let's just put a check mark on these here. You just have to interpolate to get those. Now at state 3, what do we know about state? Oh, look, we know 2 things about state 3. I bet we can get these other things. Well, what is this over here? It's called something. It's not compressed liquid. What is this at state 3?
Superheated.
What do we have at state 3?
Could you hear that?
This is
Just curious.
compressed liquid, saturated mixture. What is this?
We had someone a while ago that said superheated.
That's it. It's superheated vapor. So go with me to superheated vapor and help me find. We're trying to find 5,000 kilopascals. Hey, I see it. Superheated vapor, 5,000 kilopascals. And we want 500 C. Ooh, there it is. Well, this is easy. We just look it up. I see the little v is 0.06857. Can you find that?
Yes, sir.
Yay, good going. Now the little h is 3433, 76. And the little s is 6.97. I'm in the right place, 6.9738. Hey, look at us. We're doing great. Now, state 4. what do we know about state 4? What do we know about state 4? What is this process from 3 to 4?
Adiabatic.
Yes, it's a reversible adiabat. It's an isentrope, isn't it? And so what do I put right here in this box at state 4?
6.975.
Yay, 6.9738. Oops. 6.9738. Good going. Now, how are we going to find this?
And 9758.
Wait a minute. You could get a thank you.
We both got half of it.
Did I get the wrong number on that one?
I had said 6.975 and you had said 6.975 or 9738. And it's really 6.9758. So we both had part of it. We're getting there.
Okay, I'm gonna look it up here and see if you're right about that. 5,500. See, I'm having trouble here. Something bad happened. Wait a minute now. I'm getting there. 6.9758. It's 58, isn't it? Well, is this that has to be 58 too, doesn't it? Where did I get that number from? Well, I got it from right here. I'm looking at it. 6.975. Yeah. Yes, it's 6.9758. We're okay. Okay. Now, how do we get these here? Now let's see. Where are we? When you're in here, they call
Saturated
that
mixture.
saturated mixture. To get those, you're going to have to use this business of V4 is going to be VF plus the quality at 4 times VFG. We can look these up in the tables.
Isn't it supposed to be S?
That's supposed to be an X.
No,
He's
S.
talking about we don't know the specific volume, but we know the specific entropy.
Ah, good going. Here's what you do. You go S is equal to SF. This is at state 4. Plus the quality at state 4 times SFG.
Yes, sir.
And we know what this is, and you can look these up in the tables. And you can find the quality, and once you find the quality, you can get V4. You can also get H4. You can get H4 the same way. It's the same old stuff. It's HF plus the quality times HFG. Right? You can look that up, and we can get all of those. But now, how do we go about getting these here is the question.
First law.
Well, we're going to have to use the first law. We sure are. Let me see if I can write that. How are we coming on this class? Well, it's just about, our class is just about over. But we've covered Clausius inequality, the 3 types of cycles. Well, we didn't cover the heat pump cycle, but that's all right. You know about it. We showed you how the Clausius inequality leads to the second law. But we're going to have to use the first law to find these boxes here. I just need some room to do it. I need some room to do it. Now, the thing is, this is a control volume. This is a control volume, so you have to use the control volume version of the first law. And we're going to say that it's a steady state process, Rankine cycle. See, it's going on right now. That Rankine cycle that's burning coal is providing us with electricity right now, and it's steady state. It's the same amount of coal they're burning every hour. Well, it might vary actually, because there's peak periods. But at any given location, the energy doesn't change with time. Total energy inside your devices, whether it be the boiler or whatever, is not changing with time. And what we're going to look at right now is the pump. I need to talk to you about the pump. It's a steady state pump. It's zero. The heat transfer rate is 0 for the pump because it's adiabatic. This term here will be negative. I know there's a minus sign here, but the power is negative because you have to plug it in. Well, it actually gets its energy from the cycle, but it's not giving you energy. Pumps don't give you energy. Now we're lucky here. We can throw out the kinetic and potential terms. And from 1 to 2, we have H1 and H2. And see here, you can divide through by m dot, and what you get is this. I just need some room here to write this stuff. You get 0 equals a minus little w plus H1 minus H2. And so you can solve for little w. From 1 to 2, this little w from 1 to 2 is going to be H1 minus H2. Well, here's H1, and I showed you how to get H2. So you can get that little w. And the way you're going to get these, let me think how we're going to get those. See, from 2 to 3, there is no work done. There's no work done on a boiler. Boilers don't do any work, neither do condensers. So those are zeros. But there is a heat transfer, and you get it from the first law. And there is a heat transfer from 4 to 1. It'll be negative. See, there's a heat transfer going in here from 2 to 3. And there's a heat transfer going out here from 4 to 1. I think maybe you have enough knowledge that you could try to finish this problem for me. And what I'll do is, I'm not going to give you a grade on this. We'll be doing grades soon because I'm learning how to do it on Blackboard. But I want you to do this. I want you to finish this problem. We're almost done. And I will post the answer for you on content, and you can check your work. Let me talk to you about pumps for just a minute. And I think maybe that's enough fun for one day. Let me see if I can find this in your book here about pumps. Trying to find it about pumps. Yeah, there it is. I'm going to, I hope you took notes because I've done some of it for you. Your job for your homework is to finish this 913 for me, and I will post the answers, and you can check your work for this Rankine cycle. And if you have trouble, I'll help you when we meet on Thursday at 1 o'clock. But let me steal a few minutes from you and talk about pumps. I'm going to erase some of this. I hope you got it down. Do you understand what I want you to do? I want you to fill in these boxes. That's what I want you to do. There's only, what, about 6 or 8 boxes, and we did most of it. And I'll post the answers. Okay, I need some room here to operate. There's some room right there. That might do me. Now this material is on page 218, and we're talking about pumps right now because we have a pump. We have a pump right here. It's a, what they call isentropic pump, constant entropy pump, reversible. You're familiar with the, on a PV diagram, if you're dealing with a control mass, if you had a process that went from 1 to 2, let's say, you know that little w, that's supposed to be a little w. You know that little w is the area underneath your process because little w is the integral of PdV. And calculus tells us that's just the integral, that's just the area under your PV graph. But see, we don't have a control mass, we have a control volume. Now on page 218, they explain there's something different about control volumes. It starts on page 217, and it turns out that the little w is not equal to PDV, it's equal to VDP. If you'll turn to page, it's actually equal to, did that wrong. It's equal to negative VDP. It's on the bottom of page 217. If you'll see that on the bottom of 217. Now, you know what that is? What that is on a PV diagram, going from 1 to 2, there's state 1, there's state 2. It's the area under the graph, all right, but it's the area to the left, not under the graph. It's the area to the left. See, this is VDP. It's kind of like you took your PV graph and sort of turned it 90 degrees. You need to know that. And now, why is there a minus? Let me show you that. Pumps always do this. The specific volume gets smaller because they compress. That's what pumps do. They make the pressure bigger. See, the pressure goes up. The volume, specific volume goes down because they're compressing. And so this little, this is the specific volume. It's always plus. There's no such thing as a negative specific volume. It's always plus. Now the change in pressure in this case for a pump is always plus too. So you got a positive times a positive, which is a positive, but there's a negative in front. That makes pumps give you negative work per mass. Well, that's what pumps do. They require a work input. They don't give you work output. Turbines do, but pumps don't. Pumps have to be supplied with energy in order to function. And so that's why the minus sign is there, if that makes any sense at all. So now I've told you a little bit about pumps. I could tell you more, but that's enough. Now here's what I want you to try to do. I want you to try to finish 913, and I'll post it for you. I'll let you work on it for a while, and then I'll post it for you. So we've had fun. Is there any comment or question on any little thing before we adjourn? I want you to finish 913 the best you can, and we'll post the answer, and I'll answer your questions on Thursday. We'll be meeting again at 1 o'clock on Thursday.
Professor,
Yes.
so this is not strictly related to Thermo. In 2 other classes, I've submitted the homework that was due.
Yeah, I'm gonna give you grades on that stuff that I'm giving you grades on. You did that on my email, right?
Through Blackboard. I submitted it 2 separate ways. This is
Oh.
Ross speaking.
Oh, okay, Ross.
I submitted it 2 separate ways inside of Blackboard. I was going to see if you had a difference as far as being able to read it or not read it.
Oh,
And
thank
if
you.
one is preferable, just let me know.
Thank you, Ross. Some of the things I get, I can't read.
I know you've written it on my papers a couple times. That's why I'm asking.
Yeah, well, good. Okay, I'll look at it on both ways for you, Ross.
And then if one is better, or if they're both bad, or if they're both good, just let me know, and I can try a different way.
Okay. Well, we're going to be going the Blackboard way soon because my daughter showed me how to do that, and boy,
Yes,
it's just a whole lot nicer for me because I get all my thermodynamic stuff in one bunch,
Gotcha.
and it doesn't drive me nuts like it was.
I hear you.
Yeah. See if you can finish that, fill in those boxes. Anybody else, comment or question?
So this is correct. So there isn't any homework that is going to be due, right?
No, but I'm be looking on Blackboard because I'll probably post something maybe Saturday.
Okay, thank you.
Yeah, thank you. Any other question or comment? Okay, well, I'm going to push this little button that says end meeting. It's been fun. I hope you enjoyed it, and we'll see you on Thursday at 1. See you, some of you at another time, huh? Well, bye-bye for now, guys.
Thank you, sir.